We have two big questions to answer today. The first is, how do we find the greatest common divisor of two positive integers a and b? There are many different strategies for this, but we will be doing it with a classic ancient algorithm from Euclid. Of course, it's critical that you understand what the greatest common divisor of two positive integers even is. It's exactly what it sounds like, the greatest number which divides the two integers in question. For example, the greatest common divisor of 12 and 16, what do you suppose this is? Certainly, 12 and 16 are both divisible by 2, and we can write that like this. This says 2 divides 12, and this says that 2 divides 16. But 2 is not the greatest common divisor between these two numbers. That happens to be 4. 4 divides 12 and 16, and it is the biggest number that does so. This is an easy example because the numbers are small, but in general, how do we find the greatest common divisor of two positive integers? That's the first question we'll answer, and then we'll answer this question. How do we solve what's called a diophantine equation of this form? Ax plus by equals the greatest common divisor of a and b. Does an equation like this even have solutions in general? This equation, in the context of the numbers we were just discussing, would be 12x plus 16y equals 4. So we'll talk all about how to solve equations like that. Before we look at the algorithm for the greatest common divisor, note that the greatest common divisor of two positive integers a and b, if b divides a, then this will certainly always be b. Because if b divides a, well, of course, b divides both b and a, so it is a common divisor. And if b divides a, well, there's no bigger number that could possibly divide both a and b, because any bigger number would be bigger than b, and thus could not possibly divide b. So in this special case where one of the numbers divides the other, that number which divides the other is the greatest common divisor. Now, this very famous algorithm was introduced by Euclid in his textbook The Elements around 300 BC. Here is my pristine and beautiful copy of The Elements, by the way. Just figured I would take this opportunity to flex that. The algorithm, though, is based on this key idea. If d divides a and d divides b, then certainly d must divide their difference. D divides a minus b. This is because, of course, if d divides a, then we could write that a is equal to some multiple of d, say m times d. Similarly, if d divides b, then we could say that b is equal to some multiple of d, say b equals n times d. And then, of course, a minus b is clearly a multiple of d, because a minus b would be equal to m minus n times d. Thus, the greatest common divisor of a and b must also be a divisor of a minus b. And so we'll be able to repeatedly perform subtraction to find the GCD, and that's the algorithm. So here's our example. We're going to try to find the greatest common divisor of 108 and 30 using Euclid's algorithm, which I briefly described in concept and which you'll now see in action. The idea is that whatever the greatest common divisor of 108 and 30 is, it must also divide their difference, as we just saw, the difference being 108 minus 30, which is 78. In the same way, the greatest common divisor must also divide 78 minus 30, because we've already said that the GCD, of course, divides 30, and that it divides 78, so it must also divide their difference being 48. And we repeat this subtraction. The GCD must also divide 48 minus 30. Hence, the GCD must divide 18. Again, by the same logic, since it divides 30 and 18, it must divide 30 minus 18, which is 12. And again, it must divide 18 minus 12, which is equal to 6. This, it turns out, is the last piece of information we need, because the next step would give us 12 minus 6, which is 6, and then 6 minus 6, which is 0, which is our indication to stop the algorithm. The last non-zero number we get is the greatest common divisor of the original two numbers. One of the fascinating things about this algorithm is that the whole time we're just doing subtraction. We never actually have to find any factors of 108 and 30 to eventually find the greatest common factor of 6. So we have that the greatest common divisor of 108 and 30 is equal to 6. However, this algorithm can be improved. You may notice that a lot of subtraction was required in this case, and indeed, in larger examples, an even greater amount of subtraction may have to take place. Notice, here at the beginning, in fact, we had to subtract 30 3 times. And what is repeated subtraction? Well, in the same way that multiplication is repeated addition, repeated subtraction is basically what division is. Instead of subtracting 30 3 times and then eventually arriving at 18, we could have done 108 divided by 30, which is 3, with a remainder of 18. This, in fact, gives us a much more efficient algorithm. We could say 108 divided by 30. What does that give us? It gives us 3 with remainder 18. And we can write that like this. 108 is equal to 3 copies of 30 plus that remainder of 18. We then take 30 and 18 and do another division. 30 divided by 18 is 1 with remainder 12. So we can write that 30 is equal to 1 times 18 with a remainder of 12. And then again we do division. 18 divided by 12, that's 1 with a remainder of 6. So we have that 18 is equal to 1 copy of 12 plus that remainder of 6. And then finally, 12 divided by 6 has no remainder at all. So we can write that 12 is equal to 2 times 6, plus, of course, the remainder of 0, indicating to us that we should stop, and 6 is the GCD. Now, the simple fact that we can perform division like this, at each step getting a unique quotient and remainder, is in fact itself a result from Euclid, which we'll take for granted for this video. It's Euclid's division lemma. Now, this variation of Euclid's algorithm for finding the greatest common divisor is in fact quite efficient. It will take at most 5 times the number of digits in the smaller number steps. Taking b by convention to be the smaller number, I'll just write the number of digits of b. So this algorithm to find the greatest common divisor between a and a smaller number b will take at most 5 times the number of digits that b has steps. This measurement of the computational complexity of the algorithm is actually the result of a theorem called Lemmay's theorem, if my pronunciation attempt there is not completely horrific, and this was proven in 1844. So in this case, we could be sure that using the division method would take at most 5 times 2 or 10 steps, and of course that's an upper bound. It took us much less than that. Now, to quickly prove that this algorithm actually works to find the greatest common divisor of a and b, let's write out the process in general, and then we'll quickly see that it does indeed do what it's intended to do. Note that the first step is taking a and writing it as some multiple of b plus a remainder, just like we did in the first step of this algorithm here. Of course, we make the quotient as big as possible, and thus the remainder will be a non-negative number that's less than b. For example, if a was 7 and b was 2, we would write this as 2 times 3 plus 1. We wouldn't write it as 2 times 2 plus 3. We make that quotient as big as possible. We then do the same thing with b and that first remainder, and write b as some multiple of the first remainder, so r1 times, say, q2, and of course we have plus some other remainder, r2. After writing b in terms of the first remainder, we then write r1 in terms of the second remainder, and so have that r1 is equal to r2 times some quotient, say q3, plus a third remainder, r3. And we continue this process until the second to last step, and then finally the last step, where we get that remainder of 0. Please forgive me, in the second to last step I accidentally swapped the order of the quotient and what would be the divisor Rn minus 1. Obviously doesn't change the product, just looks a little ugly. Now remember, in the algorithm, it's the last non-zero remainder which we say is the greatest common divisor. So in this case, that's Rn. So to establish that this algorithm does what we claim, we first need to establish that this last non-zero remainder, Rn, divides A and divides B. That is, we need to prove that it is a common divisor at all. Forget greatest common divisor. First, we need to establish that it is a common divisor. And that's easy to see now that we have the steps of the algorithm written out. From this last equation, we see clearly Rn is a divisor of Rn minus 1, because Rn times this integer Qn is equal to Rn minus 1. So Rn divides Rn minus 1. But then, from the previous equation, we clearly see that Rn divides Rn minus 2, because both of these things on the right side are multiples of Rn. Rn is obviously a multiple of Rn, and since Rn divides Rn minus 1, Rn minus 1 is also a multiple of Rn. So this is a multiple of Rn, this is a multiple of Rn. Together, they give us Rn minus 2, which must also be a multiple of Rn. Hence, Rn divides Rn minus 2. We can continue this logic, eventually getting that Rn divides R1, then Rn divides B, and Rn divides A, as desired. The other thing we need to prove is that any other common divisor of A and B, say D divides A and D divides B, any other number that is a common divisor must also divide Rn. Hence, it can't possibly be greater than Rn. And indeed, we know this is true as well by looking at these equations going from top to bottom. If D is some other number which divides A and divides B, then clearly it must divide R1. If it divides B, then of course it divides this quantity here, and so it must also divide R1 in order for it to divide A. So again, if D divides B and A, then we see that it must divide R1, because it goes into this number, it goes into this number, so it must go into this number. But then we have that D divides both R1 and B, and so looking at this equation, if D goes into this number and this number, it must go into this number, R2. Then, if D goes into R2 and R1, it must go into R3. The logic continues, of course, until we get that D must go into Rn. So indeed, if any number divides both A and B, then it must divide this last non-zero remainder, Rn. With both of these facts established, we have that Rn is the greatest common divisor of A and B. It is a divisor of both numbers, and no divisor is greater than it. This algorithm even makes great sense geometrically. We'll have to use some smaller numbers so that I can show you on my graph paper, but consider the greatest common divisor of 45 and 18. If we applied the upgraded form of Euclid's algorithm using division, we would first say, well, 45 is equal to 2 copies of 18 with a remainder of 9, and then 18 is equal to 2 copies of 9 with no remainder at all. The last non-zero remainder is 9, and so we would say the greatest common divisor is 9. And we can see that geometrically. This is a rectangle, and it is of course a piece of graph paper. The dimensions of this rectangle, looking at those little squares as the units, the dimensions are 45 by 18, exactly the two numbers we were trying to find the greatest common divisor of. We can represent this first equation by covering as much of this rectangle as we can with two 18 by 18 squares. Of course, these two 18 by 18 squares don't cover the 45 by 18 rectangle completely, and there's not enough room left for another 18 by 18 square, representing the fact that there is a remainder after this division. 45 divided by 18 leaves us a remainder. But of course, the next step, 18 divided by 9, left us no remainder at all. And that's because we can finish covering this rectangle with two 9 by 9 squares. And there it is, completely covered. This means then that 9 must be the greatest common divisor of the two numbers which are the dimensions of the rectangular grid. So geometrically carrying out this algorithm, the dimensions of the smallest square that you must use to tile the rectangle is the greatest common divisor of the two numbers that describe the dimensions of the rectangle. So we know how to find the greatest common divisor of two positive integers. Now, what about the second question? How do we solve an equation like this? Ax plus by equals the greatest common divisor of a and b. Well, it turns out that once again, pretty much, we just use Euclid's algorithm. But for this, we need to use it in reverse. Consider the equation 108x plus 30y equals the greatest common divisor of 108 and 30. Perhaps the first thing we would want to do in attempting to solve this equation is finding the greatest common divisor. Of course, these are numbers we've already seen. We know the GCD is 6, and we could use our beloved Euclidean algorithm to find it. So we have that 108x plus 30y is equal to 6. As I mentioned earlier, this is what's called a diophantine equation. In particular, this one has two variables, and we're looking for values of these variables that are integers. We want integer solutions to this equation. That's what makes it a diophantine equation. And like I said, we can basically just solve this by doing the algorithm in reverse. So having already done it forwards with these two numbers to find the GCD, let's start doing it in reverse. Starting with this equation, we're going to get 6 by itself. Thus, subtract 1 times 12 from both sides. So we have that 6 is equal to 18 minus 1 times 12. Then, going back another equation in our algorithm, we can rewrite 12 by subtracting 1 times 18 from both sides of this equation. So we'd have 12 equals 30 minus 1 times 18, and we can plug that into this equation. And so we have that 6 is equal to 18 minus 1 times 12, but 12 we are rewriting as 30 minus 1 times 18. Of course, we could rewrite this a little bit. We have one copy of 18, and then another positive copy of 18 here if we distribute that negative 1. Thus, in total, it's 2 copies of 18 and minus 1 copy of 30. But 18, of course, we can rewrite using the very first equation from the algorithm. Subtract 3 times 30 from both sides, and thus we can express 18 as 108 minus 3 times 30. So 6 is equal to 2 times 18, but 18 we are writing as 108 minus 3 times 30. And then, of course, we still have the minus 1 times 30 at the end. And then finally, bringing this together, we will have rewritten the last non-zero remainder, which is the greatest common divisor, as a combination of 108 and 30. We see that we need 2 copies of 108, so 2 times 108, and then this is negative 6 times 30 minus 1 times 30, so in total, minus 7 times 30. And hopefully you see that this gives us a solution to this equation. The solution is x equals positive 2, y equals negative 7. However, this is not the only solution to this diophantine equation. In fact, we can quickly find infinitely many more. We just saw how we could replace x with 2 and y with negative 7 to have a solution. But certainly, replacing x with 2 plus 30t and y with negative 7 minus 108t, where t can be any integer, would also be a solution. Because notice, over here we would have 108 times 30t, and over here we would have minus 108 times 30t. Those would cancel out, and importantly, we'd still be left with basically x being 2 and y being negative 7, thus again giving us a solution for any integer value of t. So indeed, we have infinitely many solutions here, but do we have all of the solutions? The answer is no. Remember, we're only interested in integer solutions, so we want t to be an integer. Thus, we're not going to get something like t equals 1/2 here, but if t did equal 1/2, It just so happens in this case both of these numbers are divisible by 2, and so the solutions would still be integers if t were to equal 1/2, which again we're not allowing. But it does suggest we could rewrite this as 15t and this as negative 54t. We've just multiplied both things by 1/2, and so everything would still cancel out as we desire. In fact, not only could we divide these two coefficients by 2, we could divide them by whatever their greatest common divisor is. And we know that's 6, because those are numbers involved in this algorithm. All of these numbers have to have the same GCD, which is 6. Dividing 30 by 6 gives us 5, and negative 108 by 6 gives us negative 18. And with that, we can write the general solution. And there we have it. By letting t range over all integer values, we will get all possible solutions to this equation. And it pretty much entirely consists of using that beautiful ancient Euclidean algorithm. So that's some ancient mathematics that is still in use today. Note that in addressing this question, how to solve equations like this, we found that equations like this will always have infinitely many solutions. An integer a and an integer b, if we look at ax plus by is equal to their greatest common divisor, well, if we're looking for integer solutions, we know that we can find infinitely many of them using that Euclidean algorithm. We'll discuss what happens with equations of this form if the right side isn't the GCD of a and b another time. Let me know in the comments if you have any questions, and be sure to subscribe for more of the swankiest math videos on the internet.
From my fate, twisting to escape this. Cutting out my wrist if you can break it. Breaking in my past, I'm making it up fast. So slow down, give me the time so I can fake it. Embrace the tone of words and just how I say shit. And let me speak my poetry to your face. It's not intimate if you ain't listening. Not infinite if you ain't really into